Next up is Bruno from the University of Minho in Portugal on RISC-V virtualization based on CVA6, so a case study here. And Bruno is a PhD student in the Embedded Systems Research Group with a specialization on virtualization, mainly for embedded critical systems. So if you want to run a virtualized environment for safety critical or functional safety.
Thank you. Hi everyone, I'm Bruno. I'm a PhD student at the University of Minho in Portugal. I'm here today to talk about virtualization, more specifically on the CVA6, and how we had virtualization on the CVA6. This is my agenda. I basically just going to give you a little introduction on virtualization, the Hypervisor Extension, which is the standard that gives you virtualization support in RISC-V. And then I'll speak a bit about the CVA6 virtualization support that we did, a few enhancements that we did to the microarchitecture, and also evaluation that we did to the CVA6. So what is virtualization? Virtualization is a consolidation and isolation technology. You can basically run multiple OSs in the same hardware platform. You can think of an hypervisor is to OS, what an OS is to a process, basically. This is well used in servers, also in embedded systems for mixed criticality, to run a general purpose system with a real-time operating system to provide isolation, consolidation, and also security. The Hypervisor Extension is the RISC-V standard that gives you virtualization support in hardware. This is actually suitable for type 1 bare metal hypervisors and also hosted hypervisors. What this hypervisor extension does is basically extends the supervisor mode into a hypervisor extended mode, capable of running the hypervisor. Then it also adds two extra modes that are orthogonal to the execution, where you can run your guest OS. One of the things that is really good is basically the VS mode is actually the same as the S mode, so you can run your OS without modifications. It also adds a second stage of translation to virtualize the memory to the guest. So you have the normal translation for the guest, and then you have another stage of translation that is controlled by the hypervisor. So this is what you get when you have support for virtualization in your platform. You basically have a new mode where you have your hypervisor, and then the two other modes that I was speaking about. So CVA6 virtualization support. Basically, we have been working in providing virtualization on the CVA6. This is just an overview of the modifications that we did on the core. So basically, we had a couple of CSRs. We modified the decoder to have hypervisor instructions. We also added a new stage of translation in the Nested-MMU. So speaking about the status and features that we have so far, our implementation is actually compliant with a version 1.0. We only support 64-bit and 39-bit address spaces. We also added a couple of optimizations to the microarchitecture. Basically, we added, I'll speak a bit about this later. We also have support for the new standard interrupt controller that is the advanced interrupt architecture. Basically, this one gives us interrupt virtualization support. You can find out our open source implementation in the bottom. We also have another extension that is the timer extension. Basically, this gives us timer support to all privilege levels. So some people ask me, is this available? Yes, this is available. You can search it on the CVA6 main repo. We are working with Open Hardware Group in merging this as an optional extension. This pull request doesn't have any enhancements or timer support, the SST extension, but it's still, you have hypervisor extension. You can run your hypervisors and so on. So one of the things that we wanted to do is find out where are the bottlenecks, what we can do to improve the virtualization, and we found out that basically adding a new stage of translation adds some complexity and some performance penalties. Mainly, you have like five times more access into memory. You can see on the right, you have a picture of a full translation for a 39 scheme. Each circle is basically a memory access. The VS stage is controlled by the guest. The G stage is controlled by the hypervisor. So we came up with this solution with two-folded. Basically, we tried to add like a TLB, in second level TLB, to increase the reach and have more more entries stored. And also, we try to basically add a GTLB on the PTW, on the page table walker, just to avoid going to the G stage every time there's a TLB miss and we need to go to translate a virtual address into a physical one. So the first optimization that we tried was adding this second level TLB. This is actually very configurable, and our goal was basically then test several configurations and several parameters. You can find out also this is available online. We support both 4K, 2 mega support pages, or one or the other, or both. So the GTLB that I was talking about, this is, you can see on the right, we have a picture of what you get when you have the GTLB to make a full translation. We basically avoid going to the G stage when there is a hit on the GTLB, and then we have almost what you get when you don't have virtualization to do a full translation. This is also available online. You can use it and include it in your designs. So another thing that we wanted to do, we have all of these optimizations, so we wanted to actually evaluate it and see what we get in terms of performance. So we set up a system with a single core CVA6 using our hypervisor and a Linux as a VM. We use Mi Bench, which is has an automotive subset, which is very good for mixed criticality systems. And we use, our baseline is just the CVA6 with Hypervisor Extension, no optimizations whatsoever. So we picked up each model that we try to optimize. We pick up a few configurations that we wanted to test. And then we did, there's actually like 288 possible combinations with all of these modules. So we had to pick up what we want. So we only choose like 23 or so, something like that. Here on the table on the left, you can see that basically we can have like a design with just a GTLB and the timer support, or just GTLB. We tried all of these combinations basically. Then we wanted to do like a PPA analysis and see what's the impact in real hardware. So we chose the best ones, like that have the best performance Speedup. This is what you get in terms of results. What you see in blue is actually the baseline without optimizations. We found out that basically adding this timer extension causes a 10% increase in performance Speedup. We found out that also having a design with just GTLB and timer support, you can achieve like 9 to 16% in performance Speedup. And as expected, the full optimized design is actually achieves a maximum of 17 max performance increase. So then we did like a PPA analysis, a power performance and area analysis. We found out that basically the SSTC has a negligible impact on area. We also saw that the power is not increased by more than 5%, and our optimal design point is actually on the right side. It's basically having just a GTLB with 8 entries and a timer support. It achieves like 12.5% average speed up, less than 1% in area and power. So I spoke a little bit about this, but where is this going? I mean, we have a tape out with TII. I don't know if you had the opportunity to see it outside, but they have a booth outside. This is for UAV and drone applications. We actually put this hypervisor extension there on a real ship. And yeah, I think that's it. Yeah, thank you so much. No one has questions.
Thank you for this talk and the overview on virtualization and CVA6.